Our next topic is going back to an earlier chapter in the book, chapter 5, in which we talk about light and the nature of light. And that's really important because for stellar astronomy in particular, that's really all that we have to study. We look out in space, we see stars, but we only see the light of the stars. This is not like biology. In biology, they get a frog, they want to know how frogs work, they slice open frogs and see what dead frogs look like on the inside. In chemistry, they want to know how chemicals interact with each other. They just pour things together and see what happens. Geology wants to know what it's like inside of a rock. They break it open and look, and they do chemical analysis and so forth. For astronomy, we're stuck just looking at the light of stars. Stars are so far away, even the nearest star would take our fastest spacecraft about 76,000 years to get there. It takes years for light to get from one star to the other. And so it's a huge distance between everything. So all we can do is sit back and look. Now, that doesn't mean we can't actually do science, because we can do observations, and if we understand the physics of how light works, we can look at the kind of light that's coming from something and therefore understand what made that light, how it was made. And that allows us to find the chemical composition of stars, the temperature of stars, the size of stars, the interior structures of stars, just by understanding the physics of light and how you make light. Anyone that's been to like a Home Depot or Lowe's to buy a light bulb, there's an entire aisle of different kinds of light bulbs. It's not just different shapes, but there's different ways of making light. Each of those light bulbs is different. Each one of them makes light in a different physical process, and that light affects things in different ways. Different kinds of lights actually make things look slightly different colors. And so that's something that photographers have to realize, that the different kinds of lighting will actually make the same object look a different color under one type of lighting or another type of lighting. And so understanding all that is the first step in astronomy. So that's what we're going to do. We're going to go back to chapter 5 and talk about light. Isaac Newton experimented with light, and as Newton was looking at light, he put white light through a prism, and he saw that the different colors of light kind of break out into a rainbow. And he realized it was always the same. The least bent was always red, and the most bent was always a violet color. And so he realized he always get the same range of colors. And he actually, referred to them as red, orange, yellow, green, blue, indigo, and violet. For me personally, indigo and violet look pretty similar to me. They both look kind of purple. Okay, so I think of it as red, orange, yellow, green, blue, purple, but it's not really purple. Really, technically, violet and purple look alike, but they're different. But he used 7 because he thought 7 was a complete number. And he was into numerology and so forth, and 7 was significant to him, and so he picked 7 colors to represent these primary colors. And so it was always red was the least bent going through a prism, violet was the most bent going through the prism, green was in the middle. This was the order of the colors. For students, it's been very useful because you can imagine this is like a guy's name, Roy G. Biv, and you can remember the color. Then he got to thinking, well, what about those colors? I look at colors, like green, and there's like all these different shades of green. And so, if you were to take the green light or one of these other colors of light and run it through another prism, would it break out into little subcolors? And what he discovered was, no, it didn't. That if you had, in this diagram here, yellow light going through another prism, rather than breaking out into lots of different kinds of yellow, it took this yellow light that was bent by a certain amount in the first prism, and it bends it by the same amount here. So each of these colors is really a pure color right there. And so so that means if you were to take all these different colors and put them back together, you'd get white light. Now I wish we were in class, because this is actually a chapter that I really enjoy teaching about, because I wheel a big cart full of demos into the classroom and we demonstrate all this. So I have these projectors. I have a that projects a red spot onto the screen in the front of the room, and one puts kind of a yellow-green spot in the middle of the room, and one that kind of puts a bluish purple spot in the middle of the room, and each color is pretty much distinct, but when I put them all together, it's white light. And so it proves that, in fact, that the white light is really made up of all these different colors. Okay. Well, next question, how fast does light travel? Galileo Galilei, he's famous for pointing a telescope at the sky and realizing, oh, cool, there's cool stuff up there, and a variety of other things. But one of the things he did was he also worked with light, did some physics here trying to study how light worked. And the way he did this was he would stand on a hill somewhere, and here he is standing on a hill, and he has a lantern and a little shade on it. And he has a friend standing on another hill with a lantern and a shade. And so what Galileo did was he would uncover his lantern, and the light would travel over to the other person, who would see it, uncover his lantern, the light would travel back, and in the meantime Galileo is taking his pulse to figure out how many heartbeats it takes for light to go from one hill to the other and back. And what he discovered was it was essentially instantaneous. You know, he realized it was so fast that that was less than a heartbeat, so he had his friend stand further away and kept getting the same result. Basically, the light traveled back and forth faster than his friend's reaction time. And so Galileo concluded that light must travel instantaneously. Now, that's a wrong conclusion, but it certainly was traveling much more quickly than he was able to measure. The first real measure of the speed of light was a fellow named Ole Reaumur, and Reaumur was looking at the moon's Jupiter. Now, remember, navigation is related to where you are. I mean, in other words, what you see in the sky depends on where you are on Earth. So navigation is very closely tied to astronomy. And in fact, many of the early observatories were funded for the purpose of navigation, providing tables and charts for people that were studying, the mariners that were out at sea, and able to needed to be able to measure where they were. Now, one of the things you needed was an accurate way of telling time. And on a ship, that was very difficult to do, because the most accurate clock they had in those days was a pendulum clock. And a pendulum clock would get off if the ship was rocking. And so what Reaumur realized was that for a clock, you could use the moon to Jupiter, because Jupiter's moons go around Jupiter in a very regular pattern. So you see a moon going into the shadow behind Jupiter, and you know exactly how long it takes to go into the shadow again. And so you can calculate way into the future when this is going to occur. And so that way you'd have these tables of these events, and someone like Magellan sailing around the world would stop at an island, set up a telescope, and in order to figure out his longitude, he wouldn't have to know what time it was exactly. And so he would look at Jupiter and see exactly when this moon was passing the shadow, and he knew what time that's supposed to happen on a particular day, and so he knew what time it was. And at least he knew what time it was in England. He'd find out what time it is where he's at, and the difference in time would be related to the difference in longitude. And that worked fine with one small problem. When Jupiter and Earth were very far away from each other, the moons looked like they were moving into the shadow late. Well, why? Well, because light had to travel a farther distance. So when it's up close, it takes a certain amount of time, but if it has to go farther, then it took longer, and so you saw it happen later. And so Reamer was able to realize that it takes light about 8 minutes to go 1 AU. So that means we see the sun 8 minutes ago. When we look at the sun, we're seeing light that left the sun 8 minutes ago. And likewise, you would see the Jupiter's moons doing their things a few minutes late because the light had to travel a little bit farther to go across the solar system. And so this was the very first measure of the speed of light, 8 minutes per AU. So once they were able to figure out how big an AU was, then they had a measure of the speed of light. Speed of light is about 300,000 kilometers per second. That's 186,000 miles every second. That's the speed of light. In the calculator, the easy way of writing it would be 3 times 10 to the 8th meters per second. So this is the speed of light.